Hi, my name is Joshua Haza. I teach at Kingston High School in Washington State, and I teach physics and physical science. Today I want to show you some demonstrations we do with the kids to help them understand the physics behind waves and sound. We start off like a lot of people do with a super slinky and have the kids out in the hallway making waves and experimenting with those waves. We do have a certain setup we use I wanted to show you, so let's go outside and take a look at it. Hi, so we're out in the hallway and here's the setup we use. Basically what we have here is a 4-meter long eye. In the middle there's 1-meter increments going across to measure wavelength and distances. And then here there's 20-centimeter increments that can measure amplitude. So what the kids will do is they'll stretch one of those super slinkies out across this, and then they can make waves and they can make measurements quickly and easily using this setup. This has allowed us to actually save some of our slinkies, because the kids have a tendency to get excited and try and stretch them to 8-9 meters before you see it, and they've ruined a couple slinkies. So this is, and it also allows kids to take lots of different measurements. We use this for 3 separate labs. The first one we do is the kids investigate how the wavelength, frequency, amplitude, and tension in the slinky affects the wave speed, and they can measure that all with the stuff that's out here on the floor. Then secondly, we have them just experiment with constructive and destructive interference and types of waves. And finally, we have them do a standing wave lab where they actually use these increments to measure things like wavelength, as well as measuring frequency by counting hand movements and timing them. So it's a great way to get lots of data really quickly. It takes about 3 to 4 minutes to set up one of these stations. So it's a little time consuming, but well worth it in terms of making things move quickly in the classroom. Now for that last experiment we do with standing waves, the data we get from it isn't very quantitative. There's lots of error and it's hard to see the patterns. So let's go back in the classroom and check out some demonstrations we do to kind of help them see the pattern between harmonics. Hi, so we're back here in the classroom, and the setup I have for you right now is a standard standing wave setup using an elastic cord, but I wanted to show you with the speakers that I use. So I went to the store and got a cheap set of computer speakers, about $20. And I was able to there was 2 of these speakers that came out. I took a second speaker, cut it off, and then I pulled the wires and I connected them back to this little audio jack that I got at like a Radio Shack, so that I can plug in speakers into this speaker system and use this cheap speaker system as an amplifier to run all my audio experiments. So you can see what I've done is I've just connected this speaker. There's an elastic cord here between these 2 cables. Connected this speaker onto that cord using this wave post driver attachment you can get from Scientific suppliers online. I don't think Arbor Scientific sells it, but others do. And basically what you do is you glue that on, attach a cord to it, and you're ready to start shaking. What I've done is, to my speaker system, I've connected my iPhone, and I have an app called ToneGen Pro. I like this app. It costs a few dollars because it allows you to do a sweep function, which means I can change the frequency that's outputting to the speakers. I can change this by rolling my hand around this dial, and it's really easy to be precise with. I found that others that you have to use a slider, and it's really hard to be precise. So check it out, see what you think. So let's get this thing going and take a look at it. So again, we use this setup and we want kids to be really quantitative. We can gather really accurate data with this setup. You can see here at 15 hertz, there's not much going on the string. So all I'll do is just increase the frequency until I start seeing something happen. So right about there, I'm getting the first harmonic to set up. And this is great because I can measure the frequency very accurately. It's 20.17 hertz. We'll record that on the board, and the kids will record it in their lab journals. And then we'll measure the wavelength using a meter stick. One of the things that's really interesting is to notice what a small amplitude the speaker is vibrating at, yet we're getting a relatively large wave from that. So as we talk about standing waves, we can incorporate that idea that a small small amplitude, when it builds up on itself because it's just the right wavelength, just the right frequency, it can create this very tall standing wave. So the next thing we do is we have the kids predict what they think the next frequency will be and what the next wavelength will be. And after they've done that, we go ahead and we keep just increasing the frequency until we find it. And sure enough, right at 40.5, we get our next harmonic, our second harmonic. So then we'll have the kids then predict again the next one. And a lot of the kids will just double that one and say 80. And we get up there, and of course, we find the next one at 60. And then they have to rethink, those kids have to rethink the pattern that they found. Okay? And on this, we've gotten up to be able, we could still be able to barely see the 13th harmonic. So you can take this up quite a bit and still get really quality data from it. So that's this, this demonstration. It's great for getting really quantitative data on standing waves. All right, let's do something else. So the next demonstration we set for the kids is this one. And the question is, can we set up a standing wave and longitudinal wave, or is it only for transverse waves? So what I've done is I've hooked up a small slinky going from here to here. And I hooked it to another speaker, and I'm doing the exact same thing with the speaker, except I have a slinky attached instead of a nylon cord. And it's already running. It's probably really hard to tell in the video, but this is actually the 6th harmonic. There's a part here that's really blurry where there's a lot of motion, and there's a node right here where there's not much motion. Blurry, node, blurry, node. So